Welcome back to another Explainer, everyone. I gotta tell you, I am absolutely thrilled to share today's topic with you because we're looking at a literal frontier in artificial intelligence and academic research. We're going to explore a recent groundbreaking paper from Google DeepMind detailing their new system, Alphaproof Nexus. Now, this isn't just about an AI doing your standard everyday calculations. No way. This is about an AI system that's successfully tackling and actually solving high-level, open academic mathematical problems. We're talking about the kind of incredibly complex puzzles that have stumped brilliant human minds for decades. It's a total game changer. So let's just dive right into it with a fundamental question. Can an AI actually discover new mathematics? If you've been following the AI space at all, you probably know that large language models are, well, they're incredibly smart, but they're also kind of infamous for making really silly logic mistakes. We call those hallucinations. So you have to wonder, how on earth you trust a machine to invent new, rigorous mathematical proofs when it might just confidently make up a rule halfway through? Well, that is the exact paradox DeepMind set out to solve. To see how they did it, we'll follow a pretty clear journey today. First, we'll look at the AI math problem. Then, enter Alphaproof Nexus, designing the AI agents, cracking unsolved math mysteries, performance versus cost, and finally, the human-AI partnership. All right, let's start with Section 1, the AI math problem. What is the core limitation of using our current frontier AI models for strict academic mathematics? This really gets to the heart of the issue. While large language models are genuinely brilliant at natural language reasoning and brainstorming, they have a pretty fatal flaw for a mathematician. They are highly prone to logical hallucinations. Think of a strict mathematical proof like a massive house of cards. A mistake in just a single, unreviewed intermediate step, that'll cascade through the entire proof and completely ruin the whole shebang. You literally cannot delegate complex, rigorous math to an AI if human experts have to painstakingly verify every single line of natural language it spits out. It defeats the purpose. So, how do we fix that? That brings us to Section 2, enter Alphaproof Nexus, the incredibly elegant solution developed to overcome this massive barrier. This is Google DeepMind's Alphaproof Nexus framework. It's a highly specialized, interactive environment built entirely to guide formal proof generation with the help of an LLM. See, instead of asking the AI to write a proof in plain English, which is risky, Alphaproof Nexus literally forces the AI to write proofs in a specialized programming language designed specifically for formal mathematics. The absolute star of the show here is something called the Lean compiler. Lean is a formal proof assistant. You can think of it as the ultimate unforgiving grader. In Lean, definitions, theorems, and proofs aren't just text. They are mechanically verified code. So if an AI proposes a mathematical step, the Lean compiler executes it to see if it's perfectly logical and type-safe. It mechanically verifies every single step, ensuring absolutely zero hallucinations slip through. No way around it. If the AI tries to fake it by using a placeholder command, which Lean literally calls the sorry tactic, the compiler flags it immediately. A proof is only considered correct when it's entirely 100% sorry-free. This all builds into an automated system that DeepMind calls a Ralph loop. It works like this. In Step 1, a sub-agent powered by the Gemini 3.1 Pro model generates a proposed proof sketch. In Step 2, that unforgiving Lean compiler strictly checks the code. If it fails, which it often does, we move to Step 3. Here, the LLM actually reads the specific error message from the compiler, learns from that mistake, and refines the proof in a continuous, multi-turn cycle. It is essentially trial and error happening at lightning speed, but safely grounded by an infallible mathematical referee.
Okay, so how do you take that loop and scale it into a system capable of winning actual mathematical medals? Let's look at Section 3, designing the AI agents. What's really fascinating here is how the researchers structured 4 progressively complex versions of these AI agents. First, you have Agent A, the basic model. This is just independent subagents running that lightning-fast trial and error loop we just talked about. Then, Agent B takes that and adds the ability to query Alphaproof, which is a specialized reinforcement learning tool to help solve really tricky subgoals. Next up is Agent C, the evolutionary agent. This one is super cool. It introduces a shared database where different agents can actually share their best proof sketches using an LO rating system, kind of like chess. Finally, they smashed it all together into Agent D, the full-featured agent, combining both the Alphaproof tool and the evolutionary search capabilities.
To really grasp how that evolutionary agent works, think about this. Because a mathematical proof is binary, it's either right or it's wrong, it's incredibly hard to measure if an AI is getting closer to an answer.
DeepMind solved this by using a slightly cheaper model, Gemini 3.0 Flash, to act as a rater agent. These raters judge the plausibility, the clarity, and the novelty of incomplete proof sketches and assign them an LO rating. The system then stores only the fittest, most highly rated partial proofs in a shared database. Then the reasoning agents sample from the best ideas of their peers to guide their next search. It's literally a simulated mathematical think tank.
And that brings us to the most exciting part of this explainer. Section 4, Cracking Unsolved Math Mysteries. What happens when you unleash this full-featured agent on the hardest open problems? 56. That is the number of years that two specific problems posed by the legendary mathematician Paul Erdos had been completely unsolved by human beings. They were proposed way back in 1970, and this AI system autonomously solved them. Just let that sink in for a second. That is a massive, massive milestone for machine intelligence.
But wait, it wasn't just a one-off fluke. The system was let loose on a huge database of conjectures. It autonomously resolved 9 out of 353 open Erdos problems. It also tackled the online encyclopedia of integer sequences, proving 44 out of 492 open conjectures there. The real takeaway here isn't just the numbers, it's the sheer breadth of its capability. It didn't just master one narrow, hyperspecific niche. It successfully impacted combinatorics, algebraic geometry, convex optimization, and even quantum optics. It completely proved itself to be a highly versatile, autonomous research partner across vastly different domains.
Let me give you a really brilliant specific example. Look at Erdos problem 125. This one had been open since 1996. The problem asks about the density of the sum of two sets. One set of numbers whose base 3 representation only uses the digits 0 and 1, and another analogous set in base 4. It is an incredibly dense, tricky problem. But the Alphaproof Nexus agent, it resolved the conjecture entirely on its own by synthesizing a complex inductive thinning argument. In simple terms, it figured out how to cleverly compare how numbers behave when grouped by 3s versus 4s, a relationship known as Diophantine proximity. It broke the overarching goal into simpler sublemmas, tackled them one by one, and stitched together a flawless, machine-verified proof. Absolutely wild.
But okay, as focused learners, we have to ask the practical question here, right? We know AI compute is notoriously expensive, so let's turn to Section 5, Performance versus Cost. How much does this computational discovery actually cost to run?
The researchers ran a really interesting analysis, plotting the solve rate against the inference cost in US dollars. This tracks the 4 different agent types across several different Erdos problems. And what the data reveals is truly astonishing. To autonomously solve a decades-old mathematical problem, the compute cost was not millions of dollars. It wasn't even tens of thousands. It was literally just a few $100s per problem. Crazy, right? The surprising truth buried in that data is that Agent A, remember, that's the basic independent trial and error agent, actually solved all 9 Erdos problems on its own. And for most of the problems, it was highly cost-effective compared to the complex evolutionary models. The incredibly complex, full-featured Agent D was actually best reserved for the absolute hardest puzzles, like problem 138 and 125, where it offered massive 2x to 5x monetary savings because its shared evolutionary database kept it from wasting time in dead ends. This shows a fascinating shift. As base LLMs get smarter and smarter, simple agentic loops are becoming incredibly powerful.
Which brings us to our final section, the human-AI partnership. Because this technology fundamentally changes the role of the mathematician from a solo worker to an interactive partner.
Just look at the impact this has beyond just winning proofs. In optimization theory, the AI actually discovered a novel algorithmic parameter schedule for a gradient descent algorithm that yielded stronger mathematical guarantees. It regularly identified and fixed ambiguities or misformalizations in existing mathematical literature. And perhaps most importantly, even when the AI failed to find a full proof, it generated formal sketches that helped clarify problem structures. Because the AI writes in that strict, lean language we talked about, human experts can look at a failed attempt, immediately trust the parts that did compile, and focus their own human creativity purely on the unresolved parts.
The DeepMind paper sums this up beautifully. They wrote, "We built Alphaproof Nexus with the belief that the future of mathematics lies in human-machine partnership, where interactive AI tools serve to expand a mathematician's creative capacity." I just love that. It isn't about replacing the human researcher at all. It's about providing an untiring, rigorous collaborator that can verify ideas, generate completely novel approaches, and deepen human understanding faster than ever before.
So as we wrap up this explainer, I want to leave you with this final thought. We have literally seen an AI synthesize completely novel arguments to solve puzzles that human geniuses left open for half a century, and it did so for just a few $100 of compute. The barrier to rigorous, mathematically verified discovery has never, ever been lower. So what mathematical mystery will we solve next? Thank you so much for exploring this fascinating topic with me, and keep your curiosity sharp.